Today's seminar paper is the Array Efficient Transaction Relay for Bitcoin, and this is published in CCS 19. Everyone knows all about Bitcoin, so I'll skip about some explain about Bitcoin. So Bitcoin network can be divided into private nodes and public nodes. Normally, nodes that are blocked inbound connection by the firewall or others are called private nodes. For example, home computer nodes called about private nodes because that the nodes block inbound connection by firewall. And those that receive both outbound and inbound connection, that is reachable nodes, that they are called public nodes. So create a transaction in private and pass it to outbound connected public nodes or public nodes, create some transaction and propagate it are called flooding. That method is called flooding, and when relaying a transaction through this flooding method, this method alone uses about 18 gigabyte bandwidth per month and per node. So, and this figure shows the life cycle of a transaction. The transaction is created and signed and propagated to other nodes. Other nodes then validate the transaction and add it to the block to mining some blocks. And after the block is mined, the block is relayed and validated from other nodes. And after n more blocks follow that block, the corresponding transaction is confirmed, and this is end of transactions life cycle. A lot of people think it will take up a lot of bandwidth in the block relay, and so a lot of research has come out about block relay scenario. But as mentioned earlier, a lot of bandwidth is consumed in transaction relay, and in this paper aim to reduce the bandwidth used to relay the transaction. So transaction relay protocol, the properties of transaction relay protocol can be expressed in three ways. First, how much bandwidth does it take, and how latency it is it, and does it satisfy privacy and security. The transaction relay protocol currently used in Bitcoin is a protocol called BTC Fluid, and the bandwidth of the protocol consumes 18 GB per month, and latency takes about 3.15 seconds, and transaction announcements account for 30 to 50 of the overall Bitcoin traffic, and it achieves some privacy and security. And we aim to the bandwidth that use 18 GB per month. This is very big size, and of course Bitcoin developers are not stupid, so they don't flood the full transaction. If you know about transaction, then send the transaction hash that is 32-bit first to check if it is owned by other peers. For example, when peer 1 newly receives transaction 1 in above figure, it validates transaction and make a hash value and send that hash value through IMV message to peer 2. If peer 2 has the transaction corresponding to the hash value, this message will be ignored. But if it doesn't exist in peer 2, it requests get data message and receive the full transaction from peer 1. Full transaction is about 250 bytes, but announcement message is only 32 bytes because hash value is 32 bytes. But nevertheless, this announce IMV message is still redundant. Over 85 per second percent in message are duplicated. Since there are 8 connections, so peer-to receive the same IMV message 8 times. That means 32 times 8 is redundant. And ideally, one node would receive one IMV and one get data and one TX message per transaction. But redundant IMV messages are 224 bytes because it assumes 8 connections per one node. That means we assume only 8 connections, but there are many redundant byte messages. But we should increase the connectivity. That means it is good to increase connectivity in Bitcoin because it makes hard to isolate a node from the network. That means Eclipse attack, and it makes hard to de-anonymize transaction, link transaction to the IP address of nodes, and also it makes hard to infer the topology of the network. In other words, privacy and security are strengthened if we increase connectivity. But if we increase connectivity, the announcement cost will increase linearly, like this figure. So we have to solve this problem so nicely with some method. So there are several previous studies, but the block relay protocol is a bit different from the purpose of this paper to deal with bandwidth because the block relay protocol tries to optimize the block latency, but this paper deals with some about transaction relay situation. And topology-based routing policy is a traditional routing related methodology that is cannot be used because it is assume non-Byzantine situation. So, but blockchain assume Byzantine situation. So this is not match our problem and problem. The feedback-based approach feedbacks who has already received the information which is not safe because transaction can be traced. So feedback based approach is some easy way, but it's not much about our problem. So this paper contributes about these 3 points. First, this paper results some demonstrate that 88 of the 88% of the bandwidth used to announce transaction and around 44% of the overall bandwidth is redundant. And second is it is a combination of fast low fan-out flooding and efficient set reconciliation designed to work under the assumption of the Bitcoin network. So, and finally, early protocol reduced the bandwidth used to announce transaction by 84% immediately and allow the Bitcoin network to achieve higher connectivity in the future for better security. Looking at the erlay protocol as a whole, well-connected public nodes rapidly this well-connected public nodes rapidly fan out low fan out flooding, and each node performed this set reconciliation using minisketch. This minisketch. In other words, erlay is compromise between this flooding, which is fast but use bandwidth inefficiently, and reconciliation that bandwidth is optimal but latency is low. In other words, the core of this protocol consists of this low fan-out flooding and this set reconciliation. First, low fan-out flooding is expensive, so we should be used as efficiently as possible. Therefore, flooding should only be done with 8 well-connected outbounds, and this means only flooding public nodes that can receive inbound. In the case of set reconciliation, the goal is to find the difference between the two sets with a minimum of communication. First, I will explain about reconciliation. Here is an example of what reconciliation is and how it happens. First, A and B and C and D are connected each other, and starting with A knowing transaction number 1. A knows transaction number 1. And first, A flows the transaction number 1 to node B. And then when B receives transaction 1 by flooding, node B write a reconciliation set table. In case of A, transaction 1 was received from A, so node B record node A column as a blank. In case of C and D, transaction 1 is not transmitted by B yet, so B record this this column record transaction number 1. And let's say that this D node received transaction 2 from other nodes. So D haven't sent it to B, so D write reconciliation set as transaction number 2 in B's load in this reconciliation set. In B nodes, there are 3 timers to reconcile to A and to C and D. When this reconciliate timer is expired and then B try to reconcile with reconciliation with D node. So during the reconciliation, 2 nodes synchronize according to their local reconciliation set. So in this set, B knows that D don't have D doesn't have about transaction 1, and D knows B doesn't have about transaction 2. So they exchange the transaction, and so during reconciliation step, so node B and D knows about transaction 2 and 1, and node A knows about transaction 1. In this situation, B record transaction 2 about A and C in reconciliation set and clear about the peer 2 and about peer B. And in B situation, when reconcile with C timer is expired, then do this reconciliation as the same way. Then we need a way to find and send the difference between set efficiently without sending the entire transaction list. Here is some example about finding the set difference with PCH codes. It sends about some sketch, not an entire transaction list. First, at least estimate different set size. In this situation, at least estimate set will have 2 different sizes. So at least compute a sketch from this list. So she makes some sketch about her set, and at least send the sketch to Bob. And Bob also compute his sketch using his TX list set, and Bob XOR these 2 sketch, and then Bob can find transaction 10 and transaction 15. So Bob knows at least doesn't know about transaction 15, and Bob needs about transaction number 10. And then how is that possible? This is done through BCH sketch, and which use the sum of elements and the sum of squares about element. For example, suppose A has number 1 and 2 and 3, and B has about number 1 and 2 and 3 and 4. Since there is only one difference, so we need to find only one square summation. Thus, this summation is 6 and this summation is 10. The difference between 6 and 10 is this is 4, so a single value of this 6 and this 10 leaves a difference about number 4. But if there are two different, like 1, 2, 3, and 5, and 1, 2, 3, and 4, there are two different, the answer can be derived using the sum up to the power of 2 and summation of 1 square. So there are these 4 value, and the 4 value using their 4 value can derive the different number, these 5 and 4. And yes, and the 4 value refers to as a sketch value. So this graph shows how long it takes to decode depending on how many differences there are between sets. That is the time it takes to create some syndrome, that means sketch, calculate some different about set, and find the real different set element. There are the more different exist, that means the longer it takes to decode the mini sketch. Therefore, it is important to set this difference number, but we will not know the difference number until we know other set. So before we get other set, we need to estimate this difference number. In summary, the entire protocol of reconciliation is follow figure. First, Alice sent the size of her set A and some value about Q. This Q is derived from this equation, and then Bob received size of set A and Q value. Bob estimate D that derived from this equation and creates his sketch using this A and B and Q. In other words, it predicts the difference and makes some syndrome, that means sketch value. And Bob send this value, and Alice then find the difference between the sets from with A and B using sketch she received, and then send Bob missing 1 and missing 2 to Bob via the protocol diff exchange. If reconciliation failed due to incorrect predict of this D value, Alice makes some then these bisect messages to do this protocol reconcile bisect. Uh, if Alice requests a bisect and Bob sends sketch value with half of set his set B. And when Alice gets half set sketchy, then Alice can reconciliation each half of Bob's set and the others Bob's set. So that means Alice do a reconciliation 2 times with half of set size. If one of these is failed, then at least try the BTC flood step to get all the IMV messages. To verify the early scale better than BTC flood as the connectivity increase, we vary the number of outbound connections per node and measure the bandwidth used for announcing transaction. With BTC flood, relay bandwidth increase linearly with the connectivity because BTC flood announces the transaction on every link in the network. However, with erlay, bandwidth consumption grows significantly slower, like this, and erlay simply embraces higher connectivity, which allows for better security. In fact, if applied to current Bitcoin, erlay accounts for only 20.8%, while BTC flood account this large size about 47.6% of this size. This figure shows the probability of incorrectly measuring this, so move to reconcile bisect state and move from bisect to fallback or diff exchange. The end-to-end probability of reaching fallback is below 1%. And in this set of experiments, we kept constant the ratio between private and public types of nodes at 9:1. This is the ratio in today's Bitcoin network, and erlay has a constant latency overhead on top of BTC flow that is due to its using of matching. However, this overhead is just 2.6 seconds and changes at approximately the same rate with the number of nodes as BTC flow latency. About some yes BTC flooders latency. We choose to pay these latency overheads because this is acceptable cost to maximize bandwidth efficiency, and one of erlay's goal is to enable higher connectivity. Therefore, they analyze the latency of erlay and BTC flows for different connectivities of the network. And this graph shows some configuration of erlay-like protocols. That means change some inbound number of those nodes and change some outbound percent to flow. And these all do some reconciliation steps. And in conclusion, this erlay protocol save about 40% bandwidth for every node and allows to increase connectivity for free for Bitcoin nodes, and that leads some make network more stronger and more privacy. But there is some cons, but I think this is some minor cons. There is some latency increase. So thank you for listening my presentation.